rather. OK, let's try that again. OK, so stable matching, hopefully most of you have heard of. Right? So think of a setting where we're matching students to schools, and we have a few pieces of information. One, we know the students' preferences, so a ranking of schools. Two, each school has a maximum capacity, maximum number of students that they can take. And three, the schools also have priorities, which they use whenever the number of applicants exceeds their capacity to sort of decide which students to choose. Right? And so given these pieces of information, we now want to find a matching that has nice properties. It's stable, which you can also interpret in this context as feasible, non-wasteful, and respecting priorities. So I'm not going to go into the detail of that definition, but what is well known is that you can use the deferred acceptance algorithm of Gale and Shapley to find a stable matching in this context, and it's been widely used all over the world. Right. So you probably also know that there's like hundreds and hundreds and hundreds of follow-up papers on stable matching in various contexts. Despite all of these papers, I claim that there are a lot of things about stable matching that we don't understand very well. Right, let me give you just one example. Let's consider a very simple setting with random preferences and priorities as follows. So I have n schools. Each school has some capacity C. Okay? And I'm going to have row n students. Right? Now, if you want, you can think of C equals 1 and row equals 1 so that we have a balanced 1-to-1 random market. That's totally fine for this purpose. Let's say that each student is going to list L schools uniformly at random from this market of n. Right? And let's say that schools are going to use independent lotteries to rank these students. And then we're going to run Gale and Shapley's deferred acceptance algorithm. And we just want to know kind of what happens. What does the outcome look like? So specifically, because students are not submitting complete lists, some students may fail to match, right? They may be rejected from every school on their list. So I might want to know how many students will that be? Okay. I might also want to know, like, how does the answer depend on the length of student lists? Intuitively, the more schools that students list, the fewer of them should end up going unassigned, but sort of what is the functional form of that dependence? And also, I just sort of arbitrarily put up independent lotteries for schools. In practice, we could imagine many ways of determining priorities. So how would the answer to these questions change if we, for example, change the priority structure? I think all of these are like very natural theoretical questions. They also have analogous sort of questions in practical contexts. And the problem is when I started thinking about this, which was back in about 2014, I couldn't find any answers to these questions. Right? There really weren't many papers, if any, that allowed me to understand that. Now, since then, there has been some related work in random matching markets. So here's some closely related papers. But fundamentally, analyzing finite random matching markets is really hard. And so these papers generally make fairly restrictive assumptions and also will provide sort of loose bounds, but usually not an exact characterization of what's going to happen. Okay. So there is an alternative that has been come up with, which is Azovito and Leshno's Continuum model. So this is sort of, probably many people have encountered this phenomenon where analysis that's hard in finite settings becomes easier if you work in a continuum. So Azovito and Leshno made this observation for stable matching. And basically, the way they characterize a stable matching is by saying, OK, we've got a set of schools, and we want to predict a cutoff score for each school. And those cutoff scores then induce a stable matching. And they show how to do this. And a lot of applied papers, either applied theory papers or applied empirical papers, have used their framework as a sort of like tool to do analysis because it's so much more tractable than the finite market. The problem is, for the setting I just gave you on the previous slide, this is going to actually give you a very bad prediction. In particular, as long as the number of seats is at least the number of students, so as long as there's enough seats for everyone, their model is going to predict that the cutoff score at each school is 0, and that every student gets their first choice. And it's going to predict that no matter how long student lists are, and no matter how you determine school priorities, as long as every student is acceptable. So this model, while it's great, and I love it, it is totally inadequate for answering the questions on the previous slide. Because just to say, why would students even list more than one school? They're guaranteed to get into their first choice. Right? And the problem here is that it's basically ignoring the stochasticity in preferences. Just by random chance, we could have several students that all want to go to the same school. Okay, so this is kind of what I encountered when I tried to answer this question. So what I ended up doing was writing a paper. That paper was recently published in Management Science. And what I do in this paper is, one, I give kind of the exact answer for how many students are going to get their first, second, third choice, and so on, as a function of market primitives. I give some generalizations for heterogeneous schools, and then I can do these comparisons between using a single lottery at each school and using separate lotteries at each school, and actually show that the second case, independent lotteries, will match more students so long as students all list the same number of schools. That's one condition. Or, for example, if students list a random number of schools, but the distribution of list length is light-tailed, that same result will go through. And I also give some conditions on the list length distribution such that that flips. So I think this is like a really cool paper. It generalizes a lot of known results and gives much sharper analysis. I definitely go check it out. But today, this is not the paper I'm telling you about. Right? So what I actually want to tell you about is what are the problems with this paper. Right? So in particular, the main problem with this paper is that it's still making pretty restrictive assumptions about preferences and priorities. So it assumes priorities are either single or independent lottery, and preferences, it assumes they come from a particular class of distributions, all of which have the property that if I tell you a student's first choice school, that's basically totally uninformative of what are the remaining schools on their list. And you can imagine in practice this is not true at all. You know, there are certain students that like certain types of schools and other students that like other types of schools, and learning what my first choice is tells you maybe quite a bit about what my second or third choices are. And so what I want to tell you about today is a truly general model that allows for much more flexible priorities and preferences while maintaining enough tractability to be interesting. Okay, so when trying to develop this model, I had sort of three goals. One, I wanted my model to accurately predict outcomes in random markets. Two, I wanted it to be flexible so that I didn't need to say, okay, assume that preferences are uniformly random, for example. And three, I wanted it to be tractable so that I could actually use it to prove theorems. Okay, so let's talk about each. I'm going to try to present evidence for you that the model I've developed has each of these three properties. Right, let's start with accurate predictions. And this slide is going to be a little bit hampered by the fact that apparently when transferring slides from Mac to PC, all the graphs get very distorted. So I'll just tell you what the idea is. So these are simulation results from the original Azovito-Leshno Continuum paper, where they simulated a market where schools have rankings of students that are correlated, but imperfectly so. So basically, there's a student quality, and their priority at each school is sort of an average of their quality and an idiosyncratic match term. And so they simulate these markets, and they ask sort of, in the random markets, what is the distribution of cutoff scores ex post? Okay? These graphs are supposed to show that. Basically, they show the 5th and 95th percentile as well as the mean of the cutoff scores. For some reason, they've been totally rescaled. And so it's going to be much less impressive when I then put this slide up here. But basically, the point is that their model will make a deterministic prediction for a cutoff score. In this setting, it predicts that the cutoff score is about 0.7. Whereas my model actually generates a predicted cutoff distribution. And so it can predict what will the 5th percentile of the cutoff score distribution be? What will the 95th percentile of the cutoff score distribution be? And if you compare the slides on the top, which are the predictions for my model, to the image in Azovito-Leshno that you can go find in the publicly available thing, then they match perfectly. If you look here, they don't match at all. But that's because you'll notice the left side here has been rescaled for some reason that is beyond me. So let's move beyond that. We could make predictions about things other than cutoff score distribution. We could make predictions about, for example, the average rank. And so this is an image from a fairly well-known matching paper by Ashlagi, Kanori, and Leshno that shows basically as you add students to the market, you get this sharp phase transition where when you go from slightly fewer students than seats to slightly more students than seats, suddenly the average rank of students jumps quite a bit. Right? And so we can overlay this graph, which is based on simulation outcomes, with the predictions from my model for the corresponding market. And that's the black line shown here. So we get very accurate predictions on average rank. And we can also do the same for example, number of matches. So here are some simulation results from another paper by Marks and Schumer. And here are the corresponding predictions for my model. And again, they match very well. So sort of proof by picture, at least, this model seems to be making very accurate predictions in settings where we didn't previously have analytical results. OK, second, I claim that this model is very general and kind of allows arbitrary preferences and priorities. So let me give you a little bit of the model. Those of you who have seen or are familiar with the Azovito-Leshno model, it should be very familiar. Right? So we have a finite set of schools. Each school has a capacity. Now, in Azovito and Leshno, this capacity is a real number, which is interpreted as sort of the mass of students that can match to that school. In this context, for simplicity, I want you to think of capacities as just being an integer. It's literally the number of students that can match to that school. Okay, students are going to be defined by two pieces of information. One is their preferences, given by a ranking over the schools and the outside option of going unmatched. Another is a vector of priority scores. So these are numbers between 0 and 1. And a higher number means you have higher priority at the school. Right? And so overall, this defines a type space of possible student types. And we can imagine having a measure over this type space, which sort of gives the distribution of outcomes. And I'm going to allow this eta, this measure, to be sort of completely arbitrary. So I can encode arbitrary correlation between preferences and priorities or preferences at different schools. The only restriction I'm going to impose is a strict priorities assumption. So essentially, you shouldn't have a positive measure of students that all have the same priority at a given school. OK, and so given this information, so these are the primitives of the model. And now what I need to do is I need to generate a prediction somehow for what's going to happen in this market. And so specifically, I want to predict a distribution of cutoff scores for each school and a distribution of match outcomes for each student type. So specifically, the cutoff scores I'm going to describe through an admissions function. So you can think of AH of P as giving, for a given school H, if I have a student that has priority P at that school, what is that student's chance of getting in? This is actually what students want to know in practice, right? My priority is 0.6, or I'm in whatever priority tier. What is my chance of getting in? And so in the Azovito-Leshno model, the predictions they make are 0, 1, right? They have a cutoff score. If your priority is below that cutoff score, you have no chance of getting in. If your priority is above that cutoff score, you're certain to get in. But maybe it's more realistic to think that this should be some continuous function of your priority, given the randomness in other students' preferences and priorities. Right? And so the way I'm going to generate my prediction is basically by noting that there's three sort of equivalent ways of describing a stable matching. One is through these admissions functions, right, which give the answer to the question students want to know, which is, here's my priority. What is my chance of getting in? From this, I could predict a matching, which is, where are students likely to go? Right? So if you have a 30% chance of getting into your first choice and a 50% chance of getting into your second, then your chance of actually going to your second is, the chance that you don't get into your first times that you do get into your second. Okay? And the third sort of perspective is the interest function, which is basically school's perspective. So as a school, you could imagine asking the following question. Suppose we set an admissions threshold of 85%, a score of 85, how many students would actually choose to attend on average? And so what I'm going to do is basically show there's a clear relationship between these three. And so I'll define functions mapping, if you give me any candidate admissions function, from that I'll be able to generate a fractional matching. And from that, I'll be able to generate an interest function and then back to another admissions function, which may be different from the original admissions function you gave me to start with. Right? Unfortunately, because time is short, I'm not going to give the details of this matching. It's all in of these functions. It's all in the paper. But then my definition of stability is a fixed point characterization. Oh, boy. So it's a fixed point characterization, which says when I apply this function, I should get back to the original admissions function I started with. And the sort of secret sauce in this model, I would say the true innovation, is the vacancy function, which tells you how to actually generate these probabilistic predictions. And what I show is there's different vacancy functions you can use. I allow that to be flexible, a parameter of the model. If you use a deterministic vacancy function, assuming the number of interested schools is deterministic, then you actually recover existing definitions of stability. For the simulation, or for the numerical results I showed you previously, I was assuming interest instead followed a Poisson distribution. Okay, so I've been told I'm very short on time, so I'm gonna try to wrap up very quickly. Essentially, we give a nice characterization of like when do stable matchings exist? Always. They have a nice lattice structure. Royal Hospital theorem holds. So all of these classic results from the matching literature hold for this more general model. In addition, I get theorem 3, which is not sort of a standard result in the matching literature, but it says that under pretty natural conditions, my model is going to lead to a unique prediction. And so Ron was talking about the sort of multiplicity of stable matches. In this model, we get a unique prediction. And so that sort of explains, in some sense, the empirical finding that we often find a unique stable match, or nearly so. Okay, and then the last thing I wanted to show you for tractability, and I'm just going to have to breeze through this out of respect for the next speaker, is we can actually get analytical bounds from the equations in my model. So here on the left, we have bounds from Ashlagi, Kanoria, and Leshno, where they were analyzing a finite market. On the right, we have literally exactly the same bound coming out of the analysis of my continuum model. But the nice thing is actually their analysis only holds for c equals 1, whereas I give different expressions than the one shown here, but corresponding expressions for any capacity. And honestly, it's a hell of a lot easier to work with my model than it is to work with finite matching markets, which are a real pain. And then you can do the same thing for other results of theirs, and I get sort of analogous expressions there. So what I want you to take away from this is, unfortunately, you can't take away what exactly are the technical specifications of these 3 functions I described. But that this is a model that is very flexible, allows you to encode all sorts of correlation in priorities and preferences, generates accurate predictions, and is analytically tractable for analysis. There's still a lot to do here, and I really want your help. I see this model as sort of primarily a tool for matching theorists. Certainly more extensive numerical studies, but also more rigorous guarantees. I prove some guarantees for the accuracy of these predictions, but only under very specific circumstances. So a more general guarantee would be really helpful. And then, of course, ultimately, we want to use this model to understand stable matchings better. So I'll end there. Thank you.
Thank you, Nick. Any questions? Any questions in
the
virtual? Yes.
So I understand that your model is more precise than the one of Azovito and Leshno when each storage has a few seats, right? Because their approximation is good when there are a lot of seats in each storage.
Yep.
So my question was, does your model has advantages compared to theirs, even when there is a huge capacity at each storage?
So in the limit, as the capacity of each school grows,
Nick, if you could briefly repeat the question.
Oh, sorry. Yeah, so the question was, what are the advantages of the Azovito-Leshno model if capacities of every school are large? And I would say, if you really believe the capacities of schools are very, very large, it's not going to matter which model you use to predict. They'll sort of produce the same prediction. Mine will technically produce some kind of error bounds or variance. But where it's really interesting is in the case of modest-sized capacities, where we can't just sort of apply the law of large numbers and say that the realized interest is going to be close to its expectation. And there it will give you much, much more accurate predictions. Yeah. Yep.
Have you studied, or do you think your model allows to study the comparison between multi-type breaking and single-type breaking in terms of the thresholds of, in terms of the trade-off of number of assigned students and number of improvement pairs, like students who would be willing to change their assigned school in most preferred school?
Yeah, absolutely. So I do some of that analysis in the, oh, sorry, the question again was, would this model allow us to study trade-offs between, for example, the number of match students and the quality of their match? And the answer is yes. So in my paper, Lottery Design for School Choice, I actually do some of that analysis, and I illustrate that there is a trade-off. I think there are certainly more questions that could be used, more that we could understand there, especially if you go beyond the very simple structures of single tie breaking and multiple tie breaking, but to actually something more complicated and maybe more realistic. I think that would be a really fascinating open question. Yeah.
Any questions from the virtual room? Guess I don't see anything. Let's thank Nick again.